we now have the set of equations that we want to solve to represent almost any realistic case, whether it is flow with heat transfer, without heat transfer, with mass transfer, with chemical reactions, or all the things put together. We have a set of equations, and we have seen that all these equations form in that generic scalar transport equation. Now the question is, are we now equipped to deal with any real industrial problem? As far as the equations are concerned, we have already highlighted the fact that we can only deal with geometries which can be fit into the Cartesian coordinate system, or maybe stretching it a bit, we can do with the cylindrical polar coordinate system or even spherical coordinate system. But we can't yet deal with a physical system which has partly Cartesian coordinate, for example a rectangular duct, and partly spherical, for example rectangular duct containing a ball around which you have flow going through. So that kind of physical complexity is something that we cannot yet deal with, but can we deal with the corresponding equations which represent all this reacting flow type of situation? On the face of it, one would say yes, but it's not quite we are not in a position to say yes completely, because most real world flows are turbulent flows, and turbulent flows are very special. They have a special characteristics which makes it extremely difficult to make use of the kind of techniques that we have evolved, for example for the CFD techniques, to be directly applied to the calculation of turbulent reacting flows, for example, or even turbulent non-reacting flows, or even isothermal turbulent flows. And what we mean by this is that the very nature of turbulent flow is such that turbulent flow is not one dimensional or two dimensional, and it is not steady in the usual sense of a steady one dimensional flow or two dimensional flow that we can expect for a laminar flow. We cannot expect in a turbulent flow. It is inherently unsteady and inherently three dimensional. So that means that even when we are dealing with for example flow, fully developed flow, steady flow through a long pipe, cylindrical pipe, with constant pressure gradient, pressure difference between the inlet and outlet, so that we have essentially constant boundary conditions. Even then, if you were to put a probe which would measure the instantaneous local velocity at a particular point within that pipe, we would find that the velocity would be fluctuating with respect to time. And if you had two probes which are close to each other, and then if you were to record the instantaneous velocities measured by each probe, you would find that even though they should be under one dimensional flow condition, they should be recording the same velocity, we find that the instantaneous velocities will be different. So it is in that sense the flow is not two dimensional or one dimensional. There will be fluctuation if you go from one time to another time, there will be variation if you go from one point to another point, even in the direction in which there is supposed to be no mean flow, no flow. Okay. So it is this aspect that the flow is inherently unsteady and three dimensional that makes the computation difficult. But you can say we have the equations for three dimensional flow and we have the equations for transient flows. So in theory we can actually solve the transient three dimensional form of Navier-Stokes equations and get a solution. So that is possible, and in theory one can therefore say that we can deal with turbulent flow. But what is special about the turbulent flow fluctuations is that the fluctuations are very rapid in time, and that means that if you want to look at a steady flow through a pipe with a Reynolds number of say 50,000 or 100,000, which we expect to be in fully turbulent flow, we cannot say that the flow is fully developed, so we will consider the variation only in the radial direction. Because turbulence is three dimensional, we have to have 3 dimensional, we have to solve for not only the axial momentum but also for the radial momentum and the tangential momentum equations along with the continuity equation. So it becomes a 3 dimensional problem, and because the flow is transient we have to deal with the transient form of that. So the dimension of time also comes into picture, and because the fluctuations are very rapid, you need to solve with a very small delta t, and because there is equally rapid fluctuation in the spatial dimension, you need to have very small delta r, and since turbulence is 3 dimensional, that means it can exhibit fluctuations even in the axial direction even though it is supposed to be fully developed. Okay. So you need to have small delta z, small delta r, small delta theta and small delta t, and you need to do for a large number of times in order to get something like a steady flow condition. So this makes it computationally very expensive. It is not that it can't be done, it has been done, and this approach to calculating turbulent flows by directly solving the transient 3 dimensional form of Navier-Stokes equation is called direct numerical simulation of turbulence, or the DNS of turbulent flows. So that approach is feasible only when we have supercomputers at our disposal for weeks and months, and even then when the Reynolds number is not very high. So when the Reynolds number increases, the computation time required to get a turbulent flow calculation is supposed to go as Reynolds number to the 9/4. Okay, so that means that if you are looking at a Reynolds number of 10,000 and a Reynolds number of 10 to the power 5, then the computational effort would go as 10 raised to the power 9/4. So it is more than 100. So if it takes 1 day to get a Reynolds number flow simulation at 10,000, it will take 100 days to get a Reynolds number simulation at 10 to the power 5. And even 10 to the power 5 is not really industrially a large Reynolds number. If you are looking at flows in ducts in a large industrial concern, typically the Reynolds numbers may be the order of 10 to the power 6, so that would be even more. Okay. So from that point of view, approaching calculation of turbulent flows directly by the solution of the transient 3 dimensional form of the equations, which is what we can do now, okay, does not make a reasonable proposition, and one has to come up with a more efficient way of calculating it, because although it is 3 dimensional and transient, we as engineers or scientists, we probably do not need the full variation right down to the smallest time step and smallest space increment. What we may be interested in is the overall behavior. If you are looking at flow over a car, then what is the drag coefficient that we want, that we get for this particular profile. We are not interested in how the drag coefficient changes with every millisecond of the time. We would like to get only the overall behavior, and we would like to find out where specifically the flow is not good from the point of view of drag coefficient, and where we can make changes. We are not looking at variation of velocity at every millimeter or every fraction of a millimeter with every fraction of a millisecond time. So that is the kind of information you would be generating from a fully transient 3 dimensional flow calculation of turbulent flow with very small delta t, delta x and all that, and most of that information is useless because we are interested only in the average quantities. So that kind of solution, even though we can get in principle, is not a good thing, and there are also difficulties associated with the CFD type approach that we have discussed here, where we are using first order or second order accurate approximations for the derivatives. Usually this brings these kind of approximations, low order of accuracy approximation, brings in artificial effects of dissipation and so on, which will damp out, or which may damp out or further accentuate the dissipation that is present in natural turbulent flow through a natural mechanism. So one has to have highly accurate numerical schemes to do the discretization of the governing equations in order to get accurate estimates of the velocity fluctuations. So on the whole, the direct numerical simulation of turbulence is a proposition which is not acceptable for an ordinary engineer or a scientist. They have those kind of simulations have their place. They set the benchmarks by which we can validate simpler models. They set the benchmarks and they give insight into how the flow is behaving, and thereby we can use that to derive and develop models which are lower order models, which are more amenable to computation. Okay, so that is usually that in that sense DNS is very useful, but not in the regular computation of turbulent flows. So realizing the nature of turbulent flow, which is that it is inherently 3-dimensional and fluctuating. Reynolds has proposed in 1800s itself a decomposition of a velocity at a particular point into a time average quantity and an instantaneous quantity. So using this decomposition, he has come up with an averaging approach, so that for the averaging the Navier-Stokes equations, which have the property that if you are looking at time average behavior of a particular flow, then in theory you could solve these time average equations in which the variables would be the time average quantities. That is, you are no longer saying that the solution will not give you the velocity at every millisecond. It will give you the time average value of the velocity at that particular thing. Maybe what you will see in not what you see in an instantaneous snapshot with a high resolution of the flow, but something that is taken with a long time exposure, that kind of picture. And the advantage of this time averaged approach is that if you are looking at the time averaged equations will exhibit the 3-dimensionality or 2-dimensionality or 1-dimensionality or the steady state nature of the equations. Therefore, if you are looking at fully developed steady turbulent flow through a pipe, then using the time averaged equations you need to solve only for the steady 1-dimensional form of the corresponding equation. You do not need to study, you do not need to calculate the full 3-dimensional transient equations. So there is a great advantage that is possible when you go by the time averaged approach. Okay, so that is why the standard way of approaching turbulent flows is to do the time averaging of the governing equations and thereby derive the time averaged equations. But in the process, as with any kind of averaging process, we lose out some information, and one has to give this additional information to the equations, to the time averaged equations, so that the corresponding physics of the fluctuations is properly accounted for. So all this together constitutes the subject which is known as turbulence modeling, and turbulence modeling is an ever evolving field, and it has been evolving for the past more than 100 years. And we have now a plethora of models to deal with turbulent flows, and whereas in laminar flows, for example laminar isothermal flows, we have only 4 equations for a 3-dimensional flow, namely the continuity equation and the 3 linear momentum equations. In turbulent flow we may have additional 7 equations, so we may have to solve 11 equations to represent the time average behavior of a 3-dimensional turbulent flow. But the advantage of this modeling is that all these equations fit into a generic scalar transport equation, which we know how to solve, and this kind of advance has made it possible to extend our ability to calculate flows to even turbulent flow situations, and one can readily do these days turbulent reacting flows using CFD even in complicated geometry, but there is an attendant loss of accuracy in making this these calculations, because the moment we do time averaging, the moment we do some sort of modeling of the fluctuations, we are introducing uncertainty, and therefore for turbulent flows the equations are no longer fundamental. They do not represent wholly correctly the conservation of for example the linear momentum. We have a modified form of the equation which is valid to certain assumptions, and we have another form of the same time averaged linear momentum equation which brings in other assumptions which are supposed to be better than the previous assumption. So in that sense you have a hierarchy of models which are progressively more accurate and which are also progressively more difficult to compute, and at some point we have to make a compromise between the accuracy that we want and the effort that we want to get a general a CFD solution. So this is the kind of interplay and the choice that comes up in turbulent flow. We will briefly look at the overall picture and approach to turbulence flow modeling. We will go up to the two equation model, which is considered as the industry standard model for turbulent flows and which has proved to be very robust. Even if it is not accurate, it is proved to be very robust in giving reasonable solutions for many turbulent flows. So once we are armed with a two equation model for turbulence, then we can say yes, we can do turbulent flow calculations of a non-isothermal reacting flow in a complicated geometry. So we will be building towards this turbulence flow and how to deal with turbulent flow within the context of computational fluid dynamics. So let us start with a recollection of our generic scalar transport equation. We have said that is dou by dou t of rho phi plus dou by dou x k dou by dou x k of say some gamma phi plus s phi. As usual, a repeated index here means summation over the three components, and here we have the phi is a scalar and it usually represents the specific quantity per unit mass of that particular thing. For example, enthalpy or linear momentum, in which case phi is nothing but v, that is the velocity, and for continuity we get phi equal to 1, so that we get the continuity equation. By substituting for different expressions for the effect, the diffusivity and the source term, we can make use of this equation to represent the continuity equation, the momentum equations, the energy equation, reacting flow equations for the species conservation equation. We note that in a species conservation equation the source term is the rate of generation Ri, and this is that diffusivity Dij, which we have said is a fairly complicated thing for a multi-component diffusion to be done exactly. And for a linear momentum equation, this becomes the pressure gradient and this becomes viscosity, and for heat conduction, for the energy equation, this may be some internal heat sources if there are any, and this becomes the thermal conductivity. And for the case of even radiative heat transfer, we can represent that as, we can add some minus del dot Qr, where Qr is the radiative heat flux. Okay, so Qr here is the radiative heat flux, and the evaluation of Qr is also done using a number of models, using number of different approaches. So that's evaluation of radiative heat transfer in CFD is a major topic of its own, and it's not as simple as the corresponding conductive heat flux, which we can write as minus k gradient of temperature. So for conduction, QC is given by this, but radiative heat transfer cannot be written as simply as that, and so that is usually brought in as an additional flux term in this particular form. So the point that we are making is that we have these kind of generic scalar transport equation which can represent all the different conservation equations that we have derived so far. In this form, these conservation equations are valid only for laminar flow. In turbulent flow, unless we make sure that the calculation procedure honors the special features of turbulent flow, this kind of method cannot be used with the conventional CFD approach. Now what we mean by turbulent flow, turbulent flow has some special features. It is fluctuating, and its fluctuations are very rapid. This is an inherent feature, and typically these are so rapid that these are not of any real interest. In the sense that typically they are so rapid that they pass over within the blink of the eye, and we don't really want to know why it is so rapidly changing and how it is so rapidly changing. These things are present. The second feature about these fluctuations is that although they are fluctuating and therefore represent some sort of instability, these are well contained fluctuations, and that is why we don't really need to know so much about this. Well contained in the sense that although they seem to be, the flow seems to be unstable and so on, it is not instability which leads to perdition, destruction, but it's definitely, these fluctuations do lead to chaos. Okay, so there is a chaotic behavior of the flow properties. When we say chaotic behavior, chaos immediately tells us that it's unpredictable, and that brings into the philosophical question as to how we can get a chaotic, unpredictable behavior from deterministic equations. So that is a strand of thought which we will not pursue, but by this chaotic behavior means that you given a particular value, for example of the velocity at this particular instant here, if the flow is turbulent, you cannot predict with a great deal of accuracy what it is going to be at the next instant of time. And similarly, because the fluctuations are not only with respect to time but also with respect to space, if the flow is laminar, then if this is the velocity here and if this is the velocity here and this is the velocity here, I can say okay, the velocity here is going to be somewhere in between this. But in turbulent flow, if I know the instantaneous values at 2 points here like this, then I will not be able to give the velocity at an intermediate point to a great deal of accuracy at that particular thing, because within the 2 points the velocity is going to change. So in that sense, there is the loss of predictability. There is an uncertain element in this turbulent flow, but since the overall fluctuations are well contained, one can still be confident about the overall behavior. So there is the inherent feature of turbulent flow, it is very rapid fluctuations which are not of real world interest, but which throw in a bit of chaotic nature of the flow properties, but on the whole they are well contained fluctuations. Therefore, it is sufficient to know essentially the steady state, the average value of these flow parameters, and it is not necessary to know all the full details of this. So that is one comfort we can take when we are dealing with real world problems. And the other thing which we have already mentioned about this is that turbulent flow is never unsteady and never steady, and never 1D or 2D, it is always 3D. Even when you have the typical assumption of fully developed one dimensional flow, fully developed flow through a very long pipe with constant properties and constant pressure gradient and so on, even then when we, in the normal case when we do not expect any variation in the flow direction, in a turbulent flow there will be variation in the flow direction. So this means that we have to solve always we need to solve the full 3D transient NS equations, the Navier-Stokes equations, and all its extensions to represent the real behavior. The other feature about turbulent flow, it is highly diffusive. Diffusive in the sense that if you put a drop of ink in turbulent flow, it very rapidly it mixes. If the flow is laminar, if you put a drop of ink and the flow is going in this direction, you can trace this thing, you can see how the ink is going along. But if it is turbulent flow, the moment you put it, it gets dispersed so quickly that there is hardly any trace of it. So this highly diffusive nature is also related to the structured chaotic behavior, structured madness in the fluctuations that we see. So this is closely related to the fact that we have lots of eddies in turbulent flow. Okay, so these eddies are like almost like mini whirlpools. They mix rapidly in that particular thing, and you have not only eddies like this, you have eddies like this, you have eddies like this, you have small eddies, you have large eddies, and then you have even larger eddies. So there's, if one were able to visualize eddies, for example by going from time domain into the frequency domain, that is the usual mathematical way of looking at eddies and spectra and fluctuations, then one would find a continual range of size. It is not an eddy of a specific size, but eddies of several sizes, and a continuous range of sizes will be present. And it is these eddies that are characteristic of turbulent flow which cause a lot of diffusion, and this diffusion that actually affects the way that the parameter is going to change. This is the equation which governs the change of the parameter phi here, and there is a diffusive component here, and turbulence by its very diffusive nature directly plays in onto this diffusive. So this diffusivity, which is essentially done by molecular type of mechanisms in laminar flow, is now aided by gross fluctuations, these eddies which are much larger than the molecular distances and mean free paths. Okay, so these eddies act like mini molecules, mini atoms, and they interact with each other, and then therefore they give rise to the turbulent transport properties like diffusivity of heat and momentum and mass and all that. So they directly play into these equations. That is why it is important to resolve this diffusive nature and quantify it in the form of the additional diffusivities coming into this, because once this is disturbed, once this is no longer due to molecular motions alone, then the whole way that the scalar phi evolves will be changed. So it is important to know this diffusivity in turbulent flow. And the final character that is of interest to us from this is that this additional diffusivity is a strong function, for example, of Reynolds number. In laminar flow we know that the Nusselt number or the heat transfer coefficient does not change with Reynolds number, but not in turbulent flow. So you can have this additional diffusivity, or for example the heat transfer coefficient or the friction factor in turbulent flow divided by friction factor in laminar flow is not a constant parameter, and it can be a factor of 10, it can be a factor of 100, it can be a factor of 1000 depending on what kind of Reynolds numbers you have. That is in simple flows. So what that means is that if your friction factor is increased by an unknown amount and by a large amount, unless you know what that increase in the friction factor is, you will not be able to size your pump properly. Okay, the pump that you say requires so much horsepower, say 1 horsepower, based on laminar flow calculations may actually be requiring 10 horsepower or 100 horsepower. Okay, similarly, if you have sized a heat exchanger and the total heat exchanger is 3 meters length, because of the higher diffusivity of turbulent flow, actually the real size may be only 1/10 of that or 1/3 of that. Okay, so you may be grossly oversizing or undersizing your process equipment dealing with the fluid flow and associated heat and mass transfer if you do not take correct account of the extra diffusivity that is coming into picture. And because it is not only extra, but how much extra depends significantly on the flow parameters like the Reynolds number and the flow geometry. It is necessary to take proper account of this and then evaluate this, and that is why we need to have the set of equations which will accurately and quantitatively describe these special features related to the fluctuating properties of turbulent flow. We cannot simply neglect these fluctuating properties because these are too rapid and they are contained and all that. When you look at the overall effect of this in terms of diffusivity and in terms of the overall transport coefficients, these fluctuations have a very large role to play, and it is necessary to resolve these things and quantify these so that we can get the proper evaluation of the scalar in this. So, and that is the purpose of turbulence modeling. These fluctuations which are not of real interest from their own sake, in their own sake, will have to be properly accounted for in the equation form, and taking into account this particular nature and also this particular nature, we derive the time average form of the governing equation, which enables us to bring in the information of these fluctuations through certain extra terms. So how do we take account of this extra diffusivity that is coming from turbulence? Although we are talking about increased heat transfer coefficient and friction factor and so on, we should realize that when you look at the actual equations that we have started out with, these are equations which are valid at every point, and in the context of a CFD these are valid at every grid point. So the turbulence that we have, the turbulence diffusivity that we have, is going to change from location to location because it is a function of the velocity, and we know that in the general case the velocity is a function of space and time. So in a transient 3-dimensional flow, the additional diffusivity that is coming from the turbulence is going to change from location to location. Even in a fully developed flow through a straight pipe, it would change on a time average basis, it would change with the radial distance. So it is not a constant additional factor, multiplicative factor that we can directly put in the equations. So we have to have a mechanism whereby we can predict the local enhancement of turbulence diffusivity that is appearing in the equations. So there are two methods for this, two approaches for this. One is of course go to the time dependent Navier-Stokes equations and then solve them in the direct numerical simulation of turbulence, which we have said is very time computer intensive, computational effort intensive. So the other more practical approach is to try to smooth out these very rapid fluctuations and then use some simpler approximate but fairly accurate models to represent the contribution coming from these fluctuations. So this is what is known as the time average approach, and we have the Reynolds time average approach is the most common for essentially incompressible fluids. So we will look at this Reynolds time averaging and the concept, and we will ultimately derive the RANS equations, Reynolds averaged Navier-Stokes equations, which will form the basis for the CFD of turbulent flows in the general case. We look at the RANS equation approach, which is the more practical approach to turbulent flow calculations. We are looking at Reynolds averaged Navier-Stokes equations. This will be in terms of time averaged quantities, which enable us to solve only the time average steady state equation for a steady turbulent flow, time averaged simplified two-dimensional equations for a two-dimensional flow, and so on. For example, when we consider turbulent flow in a straight pipe under fully developed conditions, then we will be solving a single equation, which is the Reynolds averaged axial momentum equation, to resolve the turbulent velocity profile. So that is the advantage that is obtained with this. Now what is this Reynolds averaged equation? We need to understand first of all what is meant by time averaging. If you look at turbulent flow and if you plot any velocity at a particular point x0 as a function of time, u is the velocity component and t is varying in this thing, and typically what we will have is a variation quite unexpected at a particular point x0, y0, z0 as a function of time. So we are not doing anything except recording the velocity at a particular point, and this recording may be over a second, and within that second you may have these kind of fluctuations. And although I have drawn this large kind of humps like this, the variation is not even as structured as this, and if you were to take a small section here and then broaden it up, okay, if you take for example 100 milliseconds in this and then plot u versus time in that 100 milliseconds, there you will also see further squiggles. So the rapidity of the fluctuation that may be encountered is so pointed that I cannot draw it fully using a chalk piece like this. So in this context we say that this is the instantaneous velocity. If you take a particular time instant here t0, then this velocity here is the instantaneous velocity. So this is u of x0 t0. But we can define also a time average velocity at t0 by taking a time interval, say capital T, such that this whole thing is capital T. This is the time period, and we average the u over this time period centered around t0. So this distance is t by 2. So this is t0 minus capital T by 2, this is t0 plus capital T by 2, and the time average velocity denoted by u bar at x0 t0 is written as 1 by t of u dt between T naught minus capital T by 2 to T naught plus capital T by 2. So this is the average velocity that we obtain at T naught. Now what is this capital T here? This is the time period, it is the time window over which we are averaging, and this time window is such that it is sufficiently large to smooth out the turbulent like fluctuations that we have here, but it is not so large, so wide that it will suppress inherent time dependence of the system itself. For example, if you are looking at the temperature at a particular spot for a meteorological application, for weather related application, then the temperature is going to change from instant to instant, every second it is going to change. But what we are interested in, what is the average daily temperature, what is the average temperature at say 10 o'clock in the time interval of between 8 and 12 o'clock, and how does this time average quantity, how does this temperature vary on a weekly basis, on a monthly basis, on a seasonal basis, on a decadal basis, and even on a century basis in these days when we are interested in the global warming and situations like that. So we are interested not in the second by second variation of the temperature, but we are averaging over say 1 hour and then getting a value of the temperature at that location, and we take this as the average temperature represented on that particular day, and then we do the same thing next day, and these are the time averaged temperatures recorded at that particular location on a day by day basis. So this is that kind of time averaged velocity, and using this we can write the instantaneous velocity at x naught t naught as a sum of two quantities, that is the time average quantity plus a fluctuating component u prime at x naught t naught. Now what are these things? Obviously this was the u at x naught t naught here, and the average velocity may be this one. So this value here is the average velocity over, which is averaged over this thing, and the difference, what is left out of u naught after the averaging, so that is this much here, this interval. So this interval is u prime of x naught t naught. So the total velocity u at x naught, the instantaneous velocity is decomposed into the average velocity plus a fluctuating velocity, and in this particular case we can see that the fluctuating velocity component is less, is negative, okay. And in general over this time period of t naught minus capital T by 2 and t naught plus capital T by 2, we will find that the fluctuating component will be both negative and positive, and when averaged over the entire interval that we are looking at, the time average quantity will be 0. Okay, so the fluctuating component will be 0. So that is u prime dt between t0 minus capital T by 2 to t0 plus capital T by 2 is 0. So sometimes it is negative, sometimes it is positive. So for example here this is u prime and that is positive, and this is negative. So if the averaging is done correctly, then it will be such that the time average of the fluctuating component over that interval, averaging interval, will be 0, and we can decompose the instantaneous velocity into time average velocity and the instantaneous velocity. Typically in turbulent flows this instantaneous velocity is not large, and one could represent a root mean square velocity, root mean square quantity, so that is u prime square if you take n different samples, you take the ui square, ui prime square, you square each of them, sum it, and then divide by n. So that gives you the root mean square value of this, and root mean square means that this is square root of this. And we can say that typically u RMS by u average at a particular point is between 0.5 to 0.1 or even less. Okay, it's of this particular order. Okay, so the fluctuation is not like 50% fluctuation and 100% fluctuation and so on. The true turbulent fluctuations that one would record will be only of the order of 5 to 10% or even 2% and so on. But these small fluctuations are big enough to cause a 10-fold increase in the friction factor or even a 100-fold increase in the friction factor and heat transfer coefficients and mass transfer coefficients. And the 10-fold or 50-fold or 4-fold depends on the particular point of time and point of space that we are considering in a particular flow, and that is what is of interest here. So now what we can using this decomposition of velocity into an average velocity and a fluctuating velocity, we can do this for all quantities. So we can write u as u bar plus u prime, v as v bar plus v prime, and w as w bar plus w prime, and the other quantity that we have is p bar plus p prime. And in each case the quantity is integrated over a particular time period, and the capital time period is much greater than the slowest perturbation associated with turbulent flow, associated with turbulence, and it's much less than the typical time scale, time period of transient phenomena of interest. Okay, so there is an upper limit and there is a lower limit. So the time period has to be much smaller than the transient phenomena that we want to resolve using our equations. For example, in the case of the temperature variation, if we are interested in the daily temperature variation or a weekly temperature variation, then we cannot average the temperature over a week or a month. Obviously the averaging period has to be much less than the daily variation or the monthly variation. If we are interested in a monthly variation, the time period of averaging can be maybe over a day or maybe a couple of days, and if it's a daily variation that we are interested in, then it has to be definitely of the order of 1 hour or half an hour, like that. So depending on that, we fix an upper limit to the t, to the time period, such that we can still resolve the transient phenomena associated with the flow that we are interested in capturing, but it must also be much greater than the slowest perturbation associated with turbulent flow. And in this particular case, this kind of thing, so it must be much bigger than this, so that we can smooth out these variations. So that the smoothed out, if you were to plot u bar as now a function of time, although it is varying like this, that u bar may be varying only slowly. Okay, so the kind of variation that you are seeing here, the rapid variation, will disappear from u bar, and in the case where u bar is not a function of time, then we say it's a steady turbulent flow. It is turbulent flow, so we are expecting these kind of rapid fluctuations, but it is also steady flow because your average quantity is not a function of time, so it's steady turbulent flow. And if you have maintained a constant pressure gradient in across a pipe of a given diameter, straight pipe, and if the Reynolds number is of the order of 50,000, then we can expect the pipe to reach a steady flow condition where the time average velocity at a particular radial location will not vary with time. Okay, so although instantaneous velocity will change, the time average quantity will not vary, but if you were measuring the velocity at a different radial location, then definitely we can expect it. So if u bar as a function of generalized spatial coordinate x naught and t, okay, so this will be steady if it is not a function of time, and it will be homogeneous if it is also not a function of x naught. But anyway, that is that's point which we don't stress upon, but what we want to stress upon is that even under steady conditions, u bar, the time average quantity, can change as a function of the spatial location. So given this definition, we can show certain simple mathematical operations. For example, we can show that what we are interested in is not just in the velocities themselves. In our conservation equations, we have the gradients of the various quantities that are coming into picture, and so in order to use these things in our original Navier-Stokes equations and then bring out the time averaged equations, we should not only be able to write about u as a function of u bar plus u prime, but also about dou u by dou x and dou p by dou y and all those things. So if f is a quantity which is decomposed into f bar plus f prime, we can show that dou f by dou x, the time average of dou f by dou x is dou by dou x of f bar, and similarly if g is another quantity which is decomposed into g bar plus g prime, then we can show that the time average of f bar plus f plus g is equal to f bar plus g bar, and the time average of a scalar quantity times f is equal to the scalar quantity times f bar. Obviously the scalar is not a flow parameter, it is not fluctuating, and we can also show that the product of fg, where f and g are two parameters of the flow and therefore are exhibiting turbulent flow fluctuations, are the product of f bar and g bar. So that is the product of the time average quantities plus the time average of the fluctuating components. So we can just demonstrate it like this. We can write f as f bar plus f prime and g as g bar plus g prime, and we take the time average of this whole thing, and then we can write this as time average of f bar g bar plus time, we can expand this so that we have f prime g bar plus f bar g prime plus f prime g prime bar. This is this product, and we can apply this rule, and then we can write this as f bar g bar prime plus f prime g bar prime g bar bar plus f bar g prime bar plus f prime g prime bar. And because these are constant within the time period capital T, they are not function of time, so this will be nothing but f bar g bar, and here g bar is not a function of time within that time period in which we are doing the averaging, so this will come out of the time integral, so this will be g bar times f prime bar, and similarly this f bar will come out, so this will be f bar g prime bar plus f prime g prime bar, and so this is equal to f bar g bar, and this is 0 because we have said the integral of the time fluctuating component is 0 and this is 0 and we have f prime g prime bar. Now the question is this going to be 0? So it depends on the independence, the relative dependence of f and g. So if f and g are truly independent, then we expect this thing to be close to 0 or 0 if they are entirely independent. But if the two depend on each other, if there is some sort of relation between the two, then this f prime g prime bar can be positive, it can be negative also. And we can take a simple example to illustrate this point. For example, if f represents the number of ice creams that are sold in the evening on the beach, on the seashore, and if g represents the number of say coffee cups that are sold on the beach each day and if h represents the temperature of the day, then we can see if you plot the f and g and h every day, they are going to vary, they are going to show a typical variation because you will not be selling exactly the same number of ice creams. In a case where you have plenty ice creams to sell and plenty customers to for these things. But if you were to look at the time average quantity, then there will be some value, expected value for a particular season, and there is going to be a daily variation. But if one were to look at f prime g prime bar, then this is if we were to look at f prime h prime, this means that h is on a particularly hot day, h prime is positive. Okay, hot day means implies h prime is positive, and relatively cool day is h prime is negative, and f prime positive means more ice creams sold. By general common interest, we would, if it's a hot day, relatively hot day, we want ice cream, and if it's a relatively cool day, we'd probably like coffee. So what that means is that if you were to take the daily product of the instantaneous of that particular fluctuating component of that particular day and the temperature thing, then we can say that when h prime increases, h prime is positive, then f prime is also positive, and h prime is negative. So that is, when it's a cool day, there will be lesser than the usual number of ice creams sold, so then f prime will also be negative. So if you now take the product of f prime and h prime, it's going to be positive when h prime is positive, and it's also going to be positive when h prime is negative because f prime is also going to be negative. So when you now take the time average of this, when you average it out, you will see that this whole thing will be positive and greater than 0. This will be greater than 0. And similarly, if you were to look at g prime h prime, again by the same token, on a hot day, so that is when h prime is positive, g prime is going to be negative because we will have fewer number of coffee cups sold on that particular day. So that means that h prime positive means g prime will be negative, and h prime negative means g prime is positive. So if you now look at product of h prime and g prime, it's going to be negative when h prime is positive, and it's again going to be negative when h prime is negative because g prime is going to be positive. So in this case there is a certain relation between the fluctuation in the daily temperature and the fluctuation in the coffee cups, and the fluctuation is such that on an average basis this is going to be non-zero and it is going to be negative. Okay. If you now think of a different quantity like FGH I as the number of visitors to the museum, okay, number of visitors to the museum or number of visitors, number of workers reporting at a factory. Okay, even this I is going to change from day to day. Okay, so there is going to be I negative and I positive. I prime will be positive and I prime will be negative, giving us an average value. Okay, but if you now look at a variation of I prime and H prime together, covariation of these things, then we won't stop going to work because it's a hot day or a cool day, relatively cool day or hot day, because we may stop going to work because we are ill or because there is some sports match that is going on, or there is an interesting movie or some visitors have come, something like that. But it's not, we don't say okay, today is a bit hot, let me not go to work. So so because of that there is no linkage between whether it is a relatively hot day or cold day in terms of whether or not I go to work like this. So it may be that even on a hot day there may be more number of workers reporting to work, or there may be fewer number. So there is no strong correlation between I prime and H prime, and in such a case this is going to be close to 0. And in the case where there is absolutely no correlation between the two, then we can expect these two to be the interrelation, the correlation between these two to be exactly equal to 0. So from that point of view, when we come back to the product of the time average of the product of two varying quantities Fg here, it is obvious that the mean quantities will have a role to play in this, but the fluctuating quantities, the time average of the fluctuating quantities is not necessarily 0, it is 0 only when F and G are independent. Now in our Navier-Stokes equations we will have this kind of term, we will have this kind of term, we will have this kind of term, and we will have this kind of term. Making use of these simple relations, we can start looking at time averaging of the Navier-Stokes equations and then derive the time average form of the Navier-Stokes equations, in which the time average quantities, that is U bar, V bar, W bar and P bar, will appear as the primary variables which we would like to solve for. So